Men wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful, honor and recognition in case of success. This was an ad that Ernest Shackleton posted in a newspaper back in 1914 when he wanted to recruit people to join him on a trans-Antarctic expedition. And he had about 5,000 people come out and apply, and he took about 30 with him down to the South Pole. Now the reason I bring this up is because we could see this in our immediate future if we make a trip to Mars. Some mega entrepreneur will put a similar ad in the paper one day, and that ad would look something like this. Men and women wanted for hazardous journey, small wages, bitter cold, long months of complete darkness, constant danger, safe return doubtful. So we have to ask ourselves the key question, why? But most of us don't fall in the category of these intrepid adventurers. So why do we all want to go to space? Well, many people at this conference have talked about existential threats, such as we need to do it because of global warming or nuclear proliferation or fossil fuel shortages, overpopulation, mass extinction events, these kinds of things, to protect the species. It's a moral imperative. But when you think about it, many of these types of existential threats are actually already being translated by policies and incentives and things like carbon credits into economic incentives. And ultimately, what really makes us go to space is that it makes economic sense. That's why we do it. Now, when you think about economics, you need to start by thinking about foundations. So I show these pictures here not because I'm going to talk about building an even taller tower, but because I wanted you to embrace something that all of humanity's known for all time, that in order to build up, you need to have a strong base. We knew it in the pyramids, even the most recent structures are embodying that fundamental idea. Children with blocks have the same idea in their heads, or they learn it quickly. Well, let's look at where we are in terms of our thrust up and towards space. We have a strong base down here where we have skyscrapers and air traffic, which hold many, many people off the surface of the Earth already today. But then above that, we have our space industries with a big gap in between. And the space industries support a little bit of science above that. How do we get there today? We get there with rockets. I want to talk a little bit about that foundation, and I want to talk a bit about rockets. So let's start with the foundation. In our foundation today, we've got skyscrapers. They do very well. They put people in these buildings because it's prestigious, people don't turn over, it saves them a lot of money in their companies. That's the fundamental reason skyscrapers are built. And it's a very big business, it's successful. Airlines are similarly doing very well. Right now they support over 700,000 people in the air above us at any given time. And the airline industry has made recently over $700 billion of profit per year. And you think about it, you divide those two numbers out, you end up with the space that you take up when you're sitting in an airplane, on average that's worth $1 million a year, that little bit of floor space. Well, how about rockets, the thing we're using to get across that gap we have right now in the pyramid? Rockets started out strong. The red in this diagram is the failed launches. You see they've come down over time. And the green is the successful launches. You notice, though, that since the 90s, they've been kind of trending downwards. Now, if you look at human spaceflight, it's a similar kind of story. In the 90s, it peaked. In the 2000s, it started coming down. In the 2010s, we're even lower. If you project to the end of the 2010s, we're probably going to be around half of the number of humans being launched into space as we had in the 2000s. All right, so let's look at this diagram some more. What we really need to do is build something in here. And we do that, our space industries can start to grow on that foundation, and of course our space science can grow on that foundation. But the question is, what do we put in here? And what are the criteria for something that belongs in there? Is there a precedent for this? We already have perfectly good rockets taking people into space. There is. There were perfectly good ferries taking people across the English Channel and across many bodies of water between land and islands such as Prince Edward Island. But they went ahead and they built the channel anyway. In fact, they've been wanting to build the channel since the 1800s, and they only recently did it in the 80s. There's lots of large infrastructure bridges that have replaced ferries over the time. So when people invest, they think long term when they build this kind of infrastructure. Similarly, trains got replaced by highways, elaborate highway systems over the years. And more recently, this is an interesting one, even airplanes are being replaced by Maglev projects. So Tokyo and the corridor in California, for example, the two places we're talking about building maglevs to replace routes that are dominated today by airline traffic or cars. All right, so this brings us to the audacious question. Ferries that are bridges as rockets are to what? So we got to look at that space again and think, what are some criteria in the space of things that are going to place rockets? Well, if we're going to build a transportation infrastructure, it needs to offer a premium service or some kind of cost savings or some convenience perhaps, or at least be a secure investment. If you think about building a tourist destination in that space, well, then there's a lot of criteria such as it has to be safe as a skyscraper. It has to be fast and convenient to access. It has to expose us to acceptable levels of cosmic rays for tourists. When you go someplace, you need a destination, some stuff to do up there. So it needs to be like a bit like a Vegas or a Dubai in terms of its entertainment potential. I'm going to take a little side here and ask you guys if you've ever been to Waikiki. Has anybody been to Waikiki? Yes, a few people? Do you remember this pier in Waikiki? No. Okay, how about Santa Monica? Has anybody been to Santa Monica? Do you guys remember this pier? Yes, people remember the pier in Santa Monica, right? Now the reason you remember the pier in Santa Monica is because there's stuff on it to do. There's a place to go. When you build a bridge into space, it's effectively a bridge to nowhere right now, at least from an investor's perspective. We see lots of places to go, but investors think about it and they go, there's nothing up there. Why would you want to go there? So you need to build a destination at the same time you build a bridge, kind of like the Santa Monica Pier. And you need to compete in general when you build these things with amenities that are in other tourist destinations. All right, next criteria is about space access, our favorite topic. So if you're going to build something in here, we need to support a major industry, at least one disruptive new space industry. And that could be beamed solar power, it could be asteroid mining or mining the moon. It could be a major space settlement initiative. There's lots of possibilities, but it needs to support that, which means fundamentally it needs to bring launch costs way down. And as a mitigator of those existential threats, you need to be able to show that you can do things like monetize carbon credits or reduce the rate of fossil fuel consumption, reduce the proliferation of weaponizable technologies, or make it affordable for lots of people to emigrate to space. These are some criteria that would say, hey, you've got an idea here that has legs. And last but not least, in terms of criteria, it needs to be technically feasible and it needs to be economically feasible today. What can do all those things? Well, when investors look at all the existing proposals today, and there's things like space elevators and these inflated towers and launch loops and all kinds of ideas, when they look at them all, they say, no, none of these meet the criteria. And they just cross them all off and they don't get any investment. And the reason they don't get any investment is quite simple. Any investor, take a napkin and do some napkin math. They figure out what the business potential is. I looked at how much material is actually in space. This is all the material is being tracked by the Space Surveillance Network. And then I also wrote a Python script to actually tally up all the launches over time by all the countries and calculate how much payload has actually been launched into space. And that's this little red dot up here around this time frame. So it turns out that if you do this kind of analysis and figure out in the time frame you want to build your space infrastructure, what the total amount of payload is that is going to be going up into space in that time period. And so in this case, I chose an example of 2025 to 2038, which might be an investment window of interest. And I figured out that it's about 4,480 tons or metric tons are going to be launched into space in that time frame. Now, if you're an investor, you say, okay, what's the current launch price? It's $10,000 per kilogram. So you do some math and you say, oh, it's $44 billion worth of business right there. That's pretty good. But then you scratch your head and you say, well, that's where I break even. I got to make some profit. So I really want to be like a third of that in terms of my investment. And then on top of that, you hear the story about some guy named Elon who's going to launch stuff for $1,000 a kilogram. And you're like, well, maybe I should readjust my numbers. So now you're kind of getting down into the like $1 billion worth of investment if you think like that. And you think, oh yeah, there's also, so this market's already being satisfied by lots of companies that build rockets. So I'm only probably going to get a small chunk of that market. And suddenly it seems really unattractive as a business investment. So that's where you need an audacious idea to solve the problem. And this is what this is, a tethered ring. So I'm going to show you a quick video. This was made in Unity. And there's no soundtrack, I'm sorry. I can hum, though. So the Earth protrudes through this pipeline that's been built in the ocean, and these stays are attached to the surface of the Earth on the protruding side of the Earth and then tightened up, and they actually pull the pipeline, the big circular pipeline ring, they pull it away from the planet. And the reason the ring doesn't collapse is that inside the ring there's an internal mass stream, or essentially a second ring spinning around about 2 or 3 times an hour, and it's on a Maglev system, and it creates an inertial force. It's outwards. And I'll show you in a minute how this all works. Before I do, I want to kind of explain that there are these small space elevators you can use to ride up to it. So it does use space elevator technology. There'll be a marine node, as they call it in the space elevator business, where you get on the bottom of the elevator and you ride up to the top. And it's about 30 to 50 kilometers up to the top. And once you get to the top, there'll be transit systems you can use to get around on the top. So in order to draw these pictures before and make them visible, we had to make all the dimensions larger than they really are. In practice, the dimensions of these cables and rings are very fine. If you were looking at them from the ground, they would look like spiderweb would look like from about 1 meter away. So very, very thin. They'd glint in the sun, but you wouldn't see them as substantial objects. Imagine we build it around Antarctica. There would be that moving ring I talked about will spin around inside the stationary ring, and it'll generate inertial forces. So looking from the side-on view, those inertial forces will be outwards, like here and here. We're going to zoom in on the side, and we're going to zoom in some more and look at what that really looks like close up. So we have that inertial force I just described, and it's going in this direction. The force of gravity is towards the center of the planet, and the cable is attached to a point on the Earth here, and it's generating a tensile force that's in this direction. And these 3 forces are all going to add up to 0. Which essentially means, when they add to 0, it means the inertial force plus the tensile force of the tether create a vector that offsets the force of gravity. And that's what keeps it up. Now you can build this entire structure in the ocean on Earth just by laying pipeline with pipeline ships. You don't need to build it in space or anything. And after you finish building it and you speed up that internal ring, you can actually lift it into space by tightening up the tethers. So that's a major advantage of this technology over other technologies that have to be launched into space in order to become viable. They need an existing space infrastructure like heavy boost rockets, which are expensive to get them up there, which makes their cost prohibitive. This is an actual simulation based on the physics. And you can see that the ring here starts off on the ground. It looks like a side-on view and goes up. The tether is being unwound from the back of a ship, which travels towards the South Pole and pulls it up. So from the ship's perspective, it's kind of like launching a kite. Each one of these tethers is being pulled in as the ship moves forward, going kind of backwards away from the ring, and lifts it up. Now, by the magic of PowerPoint, I can turn this video on its side. So imagine there's a ship right here pulling that black wire, which is the tether. So it's pulling the tether away from the ring, and the ring is going to go up into space like that. Here's a close-up of what it looks like. In reality, we need more than one ring because of redundancy. We need to be able to take one offline to do repairs, and we also have to be prepared in case there's some sort of accident. So we have 5 rings in our plan, really, which are these objects here. And then we're going to have habitats up there, and we'll have a Maglev system that travels around the ring so people can get between the habitats, or also travel between terrestrial locations or population centers on Earth. And there's a few more details I want to quickly go through. Solar powered. There'll also be hydrogen being pumped up there as a backup system. The ring has to be mechanically isolated using pistons or something to separate it from the rest of the facilities. And the structure will be stabilized aeronautically, so that we're still in a little bit of air. There's a rarefied atmosphere up there, and that atmosphere can be used to refresh the air in the habitats, but also to provide a means of doing aeronautic stability control to keep everything where it's supposed to be in the event that there's winds or storms around. And of course, we'll need a large army of robots and drones up there to inspect and maintain this stuff because it's in the upper atmosphere where people can't breathe. I want to talk a bit about how one finances this audacious idea, because that's the key to this technology, is that it's financeable. It actually makes economic business sense. So let's start. The idea is to build it in the largest part of the Pacific Ocean, which is here, and then shift it over the population centers in the Pacific Rim. So now you can serve places like Sydney, Japan, Hong Kong, you got a little bit of China there, a bit of Russia there, the western coast of the United States, even New Zealand is serviced by this ring. So that's a large customer base. If you look at what's going on in the airline industry right now, this is a picture of all the airplanes flying around that area. There's hundreds of them at any given time servicing these population centers. Now what we want to do is build basically a maglev transit system on the ring that can take people around the ring to different destinations and bring them up on elevators and take them down on elevators. Maglevs are already becoming a new form of transportation. We're seeing Tokyo is investing lots of money to build one. Elon Musk has talked about building the Hyperloop. We believe that in the future there'll be an interconnected network of these maglevs, and we want to build one that's up in the stratosphere around the Pacific Rim to serve that market and compete with the airline industry. So let's look at how this would work. If you had a passenger going from Sydney, for example, to Los Angeles, that's the trip that you would take in the stratospheric maglev, and then this is the trip you would take in the airplane. And these are the basic numbers. So the airplane trip is much slower because it has to travel at subsonic speeds, whereas the stratospheric maglev is up in the atmosphere the upper atmosphere where there's only 0.1% air left, and it's possible to travel very quickly there. So you get a much faster trip. So there's many advantages to the stratospheric maglev idea. Unlike traditional maglevs, which cost a lot per kilometer because they're supported on pylons and they have to get land usage rights, this one's away from land and is supported by tension of cables, so it's much cheaper to support it. That makes it much cheaper per kilometer. You're so high up that it's much cheaper to maintain the vacuum compared to, say, a Hyperloop type idea. And you're above the reach of terrestrial threats, such as weather and seismic activity up there as well, so that's an advantage over some of the airlines and things like that. But there was one big question we had, and that was, if you're up near the edge of space in this transit system, are you going to expose your passengers to more space radiation than they would be getting if they were on an equivalent airplane trip? And so to answer this, we did a study that was actually sponsored by NASA Hackathon. And our study was to figure out basically how much radiation dose a passenger would get if they were in a stratospheric maglev compared to an airplane. So we got some data from NASA, and we extracted it. We had some clever guys doing that. And we came to this interesting discovery. And I've shown up here a picture which actually comes from some student work that was done in California. So if you're from Bishop, California, or anywhere near there, you should give yourself a little shout out because that was pretty cool. These guys did balloon studies, and they produced some data that's actually been supported by more rigorous scientific articles. What this graph is showing is it's showing the radiation you get versus essentially it's time this balloon was flying. But the time the balloon is flying is kind of equivalent to the balloon's altitude. I'll show it in a minute. It goes up to this point here, and then it pops, and then it comes down. What they discovered is as the balloon goes up, obviously the space radiation goes up as well. But then it reaches this maximum around here. And then space radiation starts to come down again, even though the balloon is still going up. You think, why is that? You would think the radiation should continue to go up and up and up and up and up as you get into space. Well, it turns out that the way cosmic rays enter the atmosphere and they explode and shatter and make a fiery wake of additional subatomic particles, that actually causes an increase in radiation at lower altitudes and you get a higher altitude. So there's this thing called the Pfotzer maximum, which is a place where the radiation is at its most intense in the atmosphere. And above that, you get less radiation, which I thought was very interesting. Now, airplanes typically fly around here, and our structure is going to be up pretty much where the balloon popped, up around here. So there's actually slightly less radiation if you're in a stratospheric maglev than if you're in an airplane, which is interesting. But we continued our study, and we also discovered it's much better than that, because if you think about an airplane, it goes up, flies, comes down, right? Stratospheric maglev, you go up even higher, but you come down earlier because you take your journey is a shorter period of time. And if you look at the radiation dose on an airplane, well, it kind of goes up steadily for that entire time at a certain rate. And in a stratospheric maglev, it goes up at a slightly lower rate, but it stops going up earlier because you come down, you finish your journey. And so your total radiation dose in a stratospheric maglev is actually going to be significantly less than it would be if you took the same airplane trip. And you've got all the bases covered on this idea in terms of why it makes sense to do this. And so our conclusion was it was a great idea. It's clear that maglev technology is poised to take on the airline industry. It's clear that it can travel higher and faster than a commercial airliner and therefore offers premium service. And despite its higher altitude, your radiation exposure is at least 50% less, maybe as much as 30% of the airplane trip. You get the shorter travel time, you're above this radiation limit, so your radiation dose is lower. And also, because you're a maglev system, you could automate a lot of the service. You don't need as big a flight crew, and it's a shorter trip, so you don't need as many staff. And so overall, your staff costs are going to go down, and your staff, which is radiation workers, by the way, their exposure is going to go down as well. So it makes it much easier to run this business. So we got here as a great idea, and the question is, how much money does the transportation industry have to throw around, and can that be useful for funding this? So let's look at some things that the transportation industry has spent money on lately. They spent $32 billion on the 787. They spent $25 billion on the A380. These are the two of the newest airplanes. Japan's Maglev high-speed rail system is going to cost $85 billion. California's high-speed rail is $70 billion. And two of the airports they built recently, one in Hong Kong and one in Osaka, Japan, both cost $20 billion each. So I looked at what the airline industry is doing in terms of making money. So this is actual hard data about the airline industry and how much money they make each year. So lately they're making upwards of $750 billion a year. If you project outwards into this time frame, that's these light blue lines. Let's imagine that in this time frame, starting around 2025, we cut into their business with our Pacific maglev system and started getting some money from the airline industry. We got so 5% of their overall business that's supposed we could achieve, right? So what is that 5% worth? If we took all those values and put them back into, say, $2020, which is maybe when an investor would probably start considering this, what's that worth? Well, if you know your present value economics formulas, turns out it's worth $544 billion in today's dollars. So if you invested $544 billion today into this scheme, you would break even in 2038. For infrastructure projects, that's pretty good. Not that saying that's going to cost that much, but that's how much potentially you could make. But that's not the only thing. There's a lesson to be learned in history. The London Bridge was financed partially by selling land on the top of the bridge. So let's look at what we could do if we sold our plots of land on our structure. Well, first you got to think, what's a plot of land worth up there? Well, that value of real estate depends on a number of factors, and I've listed them here. There's proximity to transportation infrastructure. We have that. Proximity to population centers. Because of the speed of our maglev, we're proximate to many population centers around the Pacific Rim. It's peaceful up there. There's great views. Some places you can see the Aurora Borealis, but definitely you can have a great view of Earth. Safety is an interesting one. I'll get to that later. There's enough real estate up there to create communities and attractions. And your expenses will be low, although I don't have time to go into why. But the big thing is anticipated future value. So you have to think, why would I buy this property and what will I be able to sell it for one day? And I'm going to get that a little bit more in a minute. So let's suppose we sold all the real estate up there for reasonable prices. Now, what's a reasonable price? Well, $10,000 per square meter is reasonable because this is what high-rise real estate sells for today. So if you sold at that price, you'd be able to sell $80 billion worth of real estate. The nice thing about real estate is people actually were willing to pay for real estate before it's even built. They pay for pre-construction real estate. Not full price, but they pay quite a bit for it. So that's like an example of how this project was funded. A bunch of sand in the ocean. A lot of money was spent on those properties, even though they weren't even built yet. So let's look at our overall investment potential. Launch services, we said there was $45 billion theoretically. I'm going to assume that if we built this thing, we capture the market because our launch costs would be so low, and that because we bring launch costs down, we'd actually be able to at least make $45 billion, but we'd be doing it because we'd be increasing the market by the same factor that we brought launch costs down. And therefore, in theory, we should be able to make $45 billion if we can really do that. But that's a bit of a skeptical one from an investor's point of view. What's more certain is that they could sell $80 billion worth of real estate, and they could perhaps get $5.5 billion of revenue from the airline industry down the road. So your total investment potential here is 2/3 of $1 trillion, which is some serious money. Investors are going to look at this and go, yeah, I'm going to check these numbers, of course, but as a first ballpark estimate, that's interesting. I'm going to go further and I'm going to study this some more. I'm going to give you some technical specifications which I don't expect you to look at, but they're here for anybody who wants to study them later. This one I want to go in a little bit more detail though. So the total population up there, 290,000 people. If you look at the potential energy cost to get up to the ring, it's tiny. Basically, it's 1 penny of energy to get to the ring itself on an elevator. To get to escape velocity from the ring is only $1.61 in energy. Now, of course, it's going to cost more because of operations costs and efficiencies and things, but potential is to be in the single digits for launch costs per kilogram. The outside pressure is down to 0.1% of an atmosphere, so it's low enough that you can launch vehicles off of this with a maglev system. The total cost of the material to build the tethers is the most expensive part of this project, and it's around $65 billion, which it's like 1/10 the total investment potential cost. The cost per person of that tether material is just $228,000, so it's like buying land in a sense, right? And keep in mind, that's the most expensive piece of the entire structure. One issue we have is that we need to build a lot of this material, which we're assuming carbon fiber here for the construction material, and it would take 28 years at our current rate of manufacture to build that much material. However, we figure for a project this size, we could probably build a few more carbon fiber factories and get the rates up. But that's just one interesting area where we discovered a small issue. All right. People like to know, well, what happens if it falls down? So we have 5 rings. If one of them fails, the moving ring will fly off into space because it's going fast enough to just leave the planet, leave the solar system, in fact. The remaining rings will still support the structure, but it'll settle a little bit lower down. If all the rings were to fail at once, though, then what would have to happen is that we'd have to dump some of the excess mass just to lower the weight. And then those aeronautic stabilization systems that I talked about would kick in. And there might even be drogue chutes as well, but they would kick in and bring you to a soft landing back on the ocean surface. And the habitats would have to be built so that if they were in the ocean, people would survive in them for long enough to be rescued. Tether failure is another possibility. What if one of the tethers breaks? So we have to make sure there's a redundancy in the sense that they overlap in real life. The picture doesn't show that. The video didn't show that, but they really have to be built so they overlap. So if one or two fails, the rest can take up the stress. By the way, there's a 2x over engineering margin in all the calculations we've been showing here. So, what else can you do with a tethered ring? Well, you can store and dispatch power in the moving ring. It's got a lot of power in there. You can transport power from one country to another very cheaply. You can perhaps house a next generation super collider. They spend a lot of money on those. So the next big one will probably fit in this structure really nicely, and we can maybe get their budget. That'd be great. But most important, I think, is that this is a stepping stone to human colonization of space. And think about it, it's not just that we're getting lower cost launch to orbit. We're also creating habitats that are kind of like space habitats. They're up in the upper atmosphere. They need to be pressurized. They're exposed to a little bit of space radiation, not as much as probably going to get on the moon or on Mars, but a little bit. And we're going to be putting a lot of people up there. And some of them are going to stay up there longer than others, and we're going to learn a lot about space medicine, our susceptibility to cosmic rays. We're going to learn a lot about making reliable systems that recycle air and maintain pressure in those environments where large volumes of people, large numbers of people. So we're going to learn a lot, and that's part of that infrastructure I talked about that gets us closer to having settlements in space, and eventually getting to the point where the planet Earth is kind of like a little heritage town in the colonization of the local region of the galaxy. All right, let's do a quick criteria review. So we talked about transportation infrastructure and some of the criteria for that. So it has to offer a premium service. Well, it's going to do that because it's way faster. It's like twice as fast as the Concorde. There's a cost savings. Yes, there's actually cost savings because there's less friction for our transportation vehicles than there are for airplanes because they're so much higher up. There's also less maintenance because these vehicles aren't going up and down all the time like airplanes do, and that's what actually wears out the airplanes. It's the constant pressurization, depressurization cycles on the fuselage. And our vehicles are cheaper because they don't have landing gear. They don't have expensive jet engines. They're just a maglev. And there's less crew, so there's less operational costs as well. Are they convenient? They're actually more convenient than airplanes because we're going to have smaller vehicles, and so they'll be leaving or departing more frequently, which means it's more convenient to get on one of these and travel around. Plus, you probably don't have to go through as much security because it's kind of hard to commandeer a maglev train relative to commandeering a plane. So there probably does going to be quicker security checks. You don't have to worry about your bottle of water anymore. You can take that with you. And being a secure investment is another criteria. Well, this technology isn't dependent on fossil fuels, whereas the airline industry is. And so if people are worried about that affecting the security of their investment, this makes it more attractive. Also, our vehicles experience minimal wear and will depreciate more slowly. And there's fewer radiation workers, and so you maybe have less concern about taking care of them in their old age. Next set of criteria, we're almost done here. As a tourist destination, it's probably going to have to be as safe as a skyscraper. On the plus side, we're too high to be attacked by a commandeered aircraft, which is a good thing. But safety really has a lot to do with our confidence in computer-aided design. But the perception of safety is an interesting other story. And I want to show you a video for this one, because it's relevant to where we are today in St. Louis. This is a bridge. It's just down by the river, near the arch. It's called the Eads Bridge. It was built in 1874. And what's interesting about it was it's the first steel bridge that was ever built in the entire world in 1874. And you think about what life was like in 1874, there was, I don't think there was any electricity around back then, not delivered to people's houses anyway. There were no cars driving around. This is 1874. Think back then, right? Put your mindset, you're in 1874, and you see this bridge some guy's just built, and he wants you to go across it to the other side of the river. Well, people back then were like, not me. I'm not going on that thing. They would not go on the bridge. And the way they solved the problem was they had to get a test elephant, and they had to get a guy with a test elephant to go across the bridge a few times so all the people could see that it could support an elephant. Anyway, after that, people were like, oh yeah, great, we can go on this bridge. And this bridge is still there today. It's standing still today, and it supports trains on top of elephants. What's really fascinating is you're thinking about this bridge and these people back in 1874 and how they were thinking about this flimsy, rickety-looking structure. And we're going to move ahead to, in a minute, it's almost there. We're going to pan around to the bridge next door, which is a more modern bridge. Look how flimsy this guy looks. This is a modern bridge. Now, if he'd built that modern bridge, it would have been much harder for anybody to accept it. So his bridge was really quite over-designed, even though at the time it looked like it was flimsy and weak. So safety, like I said, is really about perception. If the engineers build it and the CAD models prove that it's going to be safe, eventually people will start to trust it, especially if we take an elephant on it. So there's a few other things around these criteria on real estate, and I think I mentioned them. It does have to support lots of floor space so we can have a real society up there, an entertainment destination with hotels, restaurants, and lots of attractions and things to do. As a space access infrastructure, well, we've got this incredibly low launch cost, so it's going to support all these ideas, so that's great for that. Remember I mentioned that you need to think about the future value of this real estate on the ring and what it might be worth one day. Well, think about some of these industries that we're talking about here, like asteroid mining, for example. Back in, again, the 1800s, Napoleon III had these knives and forks, this cutlery set made out of aluminum. You say, why aluminum? That's crazy. Aluminum at the time was the most expensive precious metal there was. And so he did this to show how prestigious he was. Aluminum, of all things, right? And then this disruptive industry came along. It was called electroplating. And they started making aluminum cheaply, and now we use it for bicycles, Coke cans, it's everywhere. But that's what a disruptive industry can do. It can change the entire flow of an economy based on a kind of metal. And I think asteroid mining, or mining the moon, could similarly change the entire flow of a lot of money on the planet Earth if we started bringing back materials cheaply, especially exotic materials that are hard to mine on Earth or generate radiation from being mined. Now, you've got this mining industry in space. Now, who's going to make the money? Is it going to be the miners? Or is it going to be the people who serve the miners, like in the Yukon Gold Rush? It's going to be people who serve the miners. People who provide the services to them are going to make a lot of the money, most of the money, in fact. And the people who own the real estate that these services are provided on are going to make out like bandits. So that's kind of talking to the future investment value of this real estate that we've created. Finally, as a mitigator of existential threats, well, can we monetize carbon credits? Well, the answer to that is yes, because we're going to take the airline industry, we're going to replace it with Maglev technology that runs on solar power. So that's going to generate some carbon credits. Can we reduce fossil fuel consumption? Well, again, same reason. We'd actually capture the market because our launch costs would be so low, and that because we bring launch costs down, we'd actually be able to at least make $45 billion, but we'd be doing it because we'd be increasing the market by the same factor that we brought launch costs down. to obtain is potentially a threat to humanity if countries start using it for geopolitical leverage, like North Korea is today. And finally, can we make it affordable for lots of people to emigrate to space? This is more than just visiting Mars. This is talking about, let's have a whole colony on Mars, and can we support them long term? If it's only going to cost single-digit dollars to launch stuff into space, definitely we can support that. And finally, is it technically feasible and economically feasible? Well, technically, we're very close. We're using carbon fiber for our stays. We're using Maglev technology for our moving ring. There's not a whole lot more to this structure that's innovative in terms of technologies. We're all using technologies that have been extensively proven by other industries, such as the Boeing 787, which is built out of carbon fiber, or Maglevs, which are built already and serving different regions, like, for example, the airport in Shanghai uses a Maglev train. So technically, we're very close to being feasible. We obviously had to do more studies. Economically, as a ballpark estimate, we've shown that we're very feasible because we can make so much money from the airline business and also by selling real estate. So this is a technology that is not blocked by either economics or technology. I want to talk a little bit about our team. So we've been working on this since 2015, and we meet weekly. We've built up several assets besides our people. We've got computer models of the physics. We've got HoloLens models. This little thing here, if you can see it, is actually a hologram produced by a HoloLens. And a few of our team members are behind it. We've built VR experiences as well in Unity and Unreal. The video you saw was actually a recording of a VR experience. We're developing a white paper, and we need reviewers. So if any of you guys are interested in helping us to review our white paper, we'll reference your paper in it, perhaps, if we get some good ideas from you. And we have a website as well, which is at project-atlantis.com. So what are we looking for? What's a roadmap? Well, right now we're looking for people, most importantly, to help us with reviewing our white paper, to make that a really high-quality thing. So we're looking for peer reviewers to help validate our findings, people with good critical thinking skills and with some background in some of these technologies that might be relevant. We also want to set up an open-source environment so it can build out our physics models and have people work collaboratively on that. And we also want to author more mini white papers on many relevant topics. We've got about 30 or 40 topics we want additional white papers written on, such as weather and things like that. We'd like you to join us to help us solve our problems. And we want to secure some investment to help actually do some prototypes. So if you know of anybody who would be interested in having, for example, their corporate logo on one of our 3D models or 3D videos or experiences, that would be really cool. We could sort of help promote your company that way. Finally, in general, we just need people of all disciplines. Economics, people understand law, people understand investing, people understand media, programming, not just engineers. So we need everybody we can get. So to summarize, to grow as a civilization, we need new places to expand into, and we need to learn to appreciate the place that we have here on Earth. So we got a mega project here that is on the cusp of becoming both technically and economically feasible. And with that, we can do both these things. The project involves a dynamic structure, and it's called a tethered ring, and it's going to be around the Pacific Rim. And the tethered ring can support stratospheric maglevs, it can launch spacecraft, and it is itself a destination where millions can go to see our planet, the planet Earth, from a new perspective. So if you have any questions, would you mind coming to the mic so people can, or if you don't want to come up, I can repeat the question.
I still don't get how you're elevating the ring. It just seems confusing how you did it. Could you explain it?
Sure. Okay, let's have to go back.
Okay. Is it centrifugal force or something like that, or?
All right, this is a good diagram. I guess we have to start by imagining a ring. Imagine you've got a rigid steel ring, and you put it on a globe, so that it sort of sits on the globe like a crown. Okay. Now, if you tied spider webs between the edge of that ring and points on the globe, on the protruding side of the globe, all the way around, and then tighten them up with little tiny cranks, you'd be able to pull that ring off the surface of the globe, just like as if you were tightening the spokes on a bicycle wheel. Can you see that? Like the tightening, because those spokes are all at an angle. This is actually sort of an upside-down version of that, but you're pulling this direction with the spokes. You're going to pull this away from the surface of the planet this way.
Oh, I see what you mean. Okay.
Right. Well, you got to go to the mic if you're going to talk.
The tether is trying to compress the ring, and the ring is trying to expand because of centrifugal force.
Exactly. Yep.
So between the pulling it to compress it and its own desire to expand, you have a net force because they're not in line with each other.
That's right. So the force of expansion is in the plane of the ring, and the tensile force is causing it to contract is not in the plane of the ring. It's actually kind of pointing towards the pole of the planet or one side of the planet, and so it's offset. That's this line here is a tensile force. It's at an angle relative to the inertial force, and the resultant force is what offsets the force of gravity. So you have to imagine this is applying at any given point along the ring, and if you integrate that around the entire planet, it's what keeps it up. Does anybody not understand that at this point?
Can I
Ask a question? Or?
So what you're saying is that the ring is spinning.
Inside the ring, there's a spinning ring on a maglev system.
So you have a ring basically inside a tube.
Yes. There's a moving ring inside a stationary ring, which is a tube.
Right.
And
so
they're coupled by maglev.
The tube has magnets, and
Yes.
this ring is spinning on the inside, and basically the magnets are grabbing the ring,
Correct.
so to speak. And that's what's kind of keeping it up. But what is that inside ring made out of, and how big is it?
So the inside, it doesn't really matter what the inside ring is made out of, but we think it should probably be made out of ferrous material like iron or steel. But it doesn't have to be strong. It just has to be strong enough to not fall apart under the magnetic stress. This entire ring has no hoop stress of any kind, so it's just, it's too big to have any significant hoop stress anyway. So the ring doesn't have to be made out of an exotic material. Steel will be fine.
But how big is it to keep the whole structure in space? And
The
how
actual-
fast is it going?
Oh, the speed of the ring is on another slide here. The speed is 17,000 meters per second. It's going around, I think it's down here, once every 30 minutes. So it takes 30 minutes to go around once. So it's going a little bit faster than orbital velocity, but
Oh, okay. Now, how can you? Why is the delta V so low to shoot rockets off? Is it just because of the speed or because of the height?
oh, the delta V is the same, but the advantage is that because we're already in the stratosphere, we can accelerate along the top of the atmosphere on the ring and gradually build up speed on this maglev system and then release you into space, into orbital. But the delta V is the same, essentially, as you would be from a rocket. It's only slightly different potential energy because you're a little bit higher up, but that's insignificant compared to the horizontal speed you need to get to orbital velocities. The real advantage here is that you can electrically propel this vehicle with maglev technology instead of using rockets, which are subject to the rocket equation.
Yeah, thank you.
Can we bring the mic over to the lady on the right here so that she can speak? Thank you very much.
So the the maglev system is inside the ring, but you're going to let things go into space outside the ring. How do things connect to the maglev system in order to move along the ring and then get out, or along the ring and then go down to wherever you're going, airplane style?
Okay.
And for that matter, how do things get up and down that aren't planning to go, well, whether they're going to space or not?
All right, so I think, I should be more clear on that because I've used the word maglev technology a lot, but there's actually several maglev systems. So there's one maglev system that's responsible for moving the moving ring, which is inside that tube. Mm-hmm. There's a second maglev system which is responsible for transportation between the habitats that are on the ring and for providing people with the ability to go between population centers around the Pacific Rim. And there's a third maglev system which is used to launch vehicles into space. Most likely the third maglev system is actually going to be supported by the ring, but it will also have aeronautic stabilizers so that it can support itself from the acceleration of the object that's being launched. So while it's being launched, it'll actually be the maglev system itself will actually be thrusting in the atmosphere to hold itself in position, so that it doesn't actually impose forces onto the ring due to launch. So we're going to try to isolate it in that way from the ring. Otherwise, it'll kind of ripple. The forces will ripple into the ring and cause habitats to shake and things every time somebody launches something.
Thank you.
You're welcome.
Hi, I was wondering why is the Pacific region being proposed as the site rather than another place where there's more continents?
Yes, so that's a good question. So we actually looked at building one around Antarctica, like I showed in that first figure, and there's not enough business in that area, honestly, to support the ring at this point. The Pacific gives you the largest ring, and interestingly, the cost goes down as the ring gets larger in diameter due to the way the forces work. In terms of markets, you've got a much bigger market around Europe and the East Coast of the United States in terms of traffic. If you could build a ring there, you'd actually make more money, but it's just hard to build a ring there because the Atlantic Ocean isn't as big as the Pacific Ocean by a long shot, and so your ring can't be big enough, and so your ring has to be a lot more expensive to build in the ocean. But if you could build the ring on land somehow, that could be a potentially interesting market. So that's why we chose the Pacific Rim as our sort of target market for proposing how we would finance the project.
Have you considered various natural environment effects ranging from, say, electromagnetic effects, hurricanes, sea states, seismic activity, and so forth? And what have you looked at, and what's left to do on it, and what are your findings?
Yeah, so the white paper has, I would say, about 40 interesting questions just like that one, including questions like what happens if a volcano erupts nearby and there's an ash cloud that goes by, or what happens if lightning strikes the tethers. What about ice storms? There's 100 questions. Well, there's actually 40 questions like that that we've come up with so far, and I'm sure there's more. Now, each one of those is in the various stages of development, and that's why I was talking about these mini white papers. I'm not claiming that we've got a solid answer for how to de-ice the tethers and the best answer for that, for example. We've considered subjects such as, the storms, rogue waves, what would we have to engineer to make sure that our anchor points are not going to get blown away by a rogue wave, and how do we make sure our tethers are going to stay where they're supposed to be during a hurricane force wind. There have been technologies that have been developed similar to ours, such as there's these blimps that were built by NORAD, I think, that also use tethers, and they were designed to survive in storms as well. Although one of them didn't, so they need to be better. But there's engineering work that needs to be done to answer all those questions, and we are looking for experts in all those areas to tell us about past work that's been done so we can reference it, as well as what some of the criteria that have been developed to make each of these individual problems tractable to us. So we have worked on almost all of them to some degree, but none of them, I would say, is sort of ready to go completely.
Seemed that spinning ring would have an inertial moment, and the fact that the whole ring is then being spun with the Earth's rotation. Is there going to be a gyroscopic torque on this?
Yes, that's one of those questions. So it turns out that the Earth is turning very slowly. The ring is going around once a half hour. The Earth is going around once every 24 hours. Mm-hmm. So the proportion of gyroscopic force that you're dealing with compared to the simple inertial force of the ring is, I guess, 1/48th. So the gyroscopic forces that we have to control or contend with are relatively tiny, and all you need to do is just change the angle slightly of your magnets and change the angle of your stay slightly, and that problem is solved. So essentially it's just forced against a gyroscopic inertia, but it's a relatively small, so like I said, a 2% size problem, 2% size problem.
That gets taken care of by what, tightening the tethers, or?
Well, yeah, just the angles of the forces are changed by 2% by gyroscopic forces. Okay. So that would change the angle of the tether and the angle of the Maglev systems where its forces are. I guess I'm probably confusing by talking about the angle of the Maglev forces, but inside that Maglev ring, there is a slight angle due to the two angles that are coming together. So they're not exactly, the Maglev system is not exactly in the plane of the ring. It's slightly angled downwards. As a result of the way the forces work. But that's a more advanced topic. Okay. Any other questions? Well, we do have another question. Okay.
How'd you come up with such a radical idea like this?
Well, I have to give credit to the International Space Elevator Consortium in an indirect way. I was looking for something to do on a Sunday, like in 2014, I think it was, and I was online, and I found that there was an International Space Elevator Consortium, and they were actually having a conference in Seattle, where nearby where I happen to live. And I was like, "This is great! I want to go." And then I looked at the dates, and it was like they just ended. It was ending right then. So I put a reminder on my calendar to attend next year. So I thought that'd be great. So I put a reminder about 3 months in advance. And when the reminder popped up, I went onto their site, and it just happened that was the last day for submitting abstracts as well. And it turned out that speakers get to go for free. So I thought, well, I'll submit an abstract and see if I can get to go for free. So I kind of thought for a few minutes and came up with this idea. And I submitted an abstract, and they accepted it. And I was like, oh, great, now I got to come up with a paper and all this stuff. So I worked on it some more, and I wrote the paper. Luckily, I'd written the abstract in a rather abstract way, so it wasn't entirely difficult to make the whole thing. But yeah, so I developed the idea up towards the conference, and then I went to this conference thinking they were going to rip me to shreds because it had been done before, and there was some obvious reason why it wouldn't work, and all this kind of stuff. But when I got there and presented, they were, all these space elevator experts said they had never heard of this before. It seemed like it might work. They had some of the same questions you guys had, but nobody really could point to a fundamental reason why it wouldn't work. However, I didn't, at the time, I wasn't convinced it would work economically, and so we focused instead mostly on the economic side, how do you make it work economically, which is why we came up with this stratospheric maglev idea to basically fund the project. That's how I came up with the idea. Yeah. Do you want to come forward, or do we bring the mic to you? Yeah.
What altitude will you be, and if that's an altitude like about 50 okay, what altitude you will be at? Do you have a concern about electrical phenomena at that altitude? It looks like you're in the near high in the stratosphere, high stratosphere, mesosphere, where there's a lot of electrical activity, blue sprites, red jets, that type of thing.
So we're going to be so first question is what altitude we're going to be at, and so we're going to be we're actually thinking varying altitudes depending where we are in the ring, but 30 to 50 kilometers. For space launch, we might be a little higher, and for people and transit, we might want to be a little bit lower. The knowledge we have on atmospheric phenomena at those altitudes, especially electrical phenomena, is pretty close to zero, I think. So we weren't worried about lightning, but if there are other atmospheric phenomena that we should be thinking about, you should talk to me right after this and tell me about them so we can add them to the list of things to investigate. And we have heard of atomic oxygen. What were some of the other things you mentioned there?
Blue sprites, red dwarfs, jellyfish phenomena.
Jellyfish? Extreme lightning.
Extreme.
Exoatmospheric lightning. Okay, I had not heard about that. We had a plan for lightning at the ground level, but...
Transient infrared emissions.
Okay, good one. I want to learn more about these.
Yeah.
So that's great. Thanks.
I'll throw one in. V cross B spacecraft charging type effects.
V cross V spacecraft charging effects. Anybody else have any interesting phenomena?
Yes.
Go.
Plasma deionization.
Plasma deionization. We have to talk after this. This is great. This is why I came to this conference, to meet people like you. This is great. All right. Any other questions? Thanks, by the way. That was a really good question. All right. Well, I want to thank you all for sticking out to this point of the conference. It was really great that you came. I appreciate that. You're great.